Hello and welcome back to another episode from Highwater Studio. In today's episode we're going to talk about stream pollutant decay and how to calculate the concentration of a non-conservative pollutant in a downstream location. In our last lecture we looked at how to perform a mass balance equation to determine the mixed stream concentration when you have a stream with a low concentration and high flow rate mixing with a waste stream with a high concentration and low flow rate, which of course would work for any combination of streams. That's just a very typical example, and for this example we calculated a concentration of an arbitrary pollutant for 10.9 milligrams per liter. Now if you were just looking at a conservative pollutant, or we're only interested in the concentration at the point of mixing, you would basically be done. But if you want to determine the concentration for a downstream location of a non-conservative pollutant, then we need to take into account decay and create a decay model. The off-the-shelf typical way of trying to model decay is to use a first-order linear decay equation. And this is because this is very common in nature for most constituents. And what this means, this first-order linear decay, means that the rate of decay is proportional to the concentration at any instantaneous point in time. So the higher the concentration is, the faster the decay rate is. But as the concentration decreases due to decay, the rate of decay also decreases. That's where you get a differential equation. And we will first start at just looking at an already derived equation for first order linear decay. But at the very end of the lecture, we will look at how to actually derive this equation from a differential equation. So graphically looking at this situation, this example, we have our concentration at point A of 10.9 at our initial condition at time equals 0, just at the point of mixing. And we're interested in the downstream concentration at some point B, 50 kilometers downstream. And one of the things, probably the most important in terms of solving this equation, that piece of information that we're going to need is the time, right? This is going to decay over time. There's obviously a spatial and temporal relationship in mass transport. So we need to solve how long it's going to take for this contaminant to transport to location B. So we need some kind of velocity, and typically you're going to use some kind of average velocity. Open channel flow is a very complicated subject. We have different velocities at different locations across this cross-sectional area, this profile, both vertically and horizontally. The velocities are different. You also tend to often have a tortuous path when you have turbulent flow, so you're not actually getting a straight line of transport. So the time that it takes to transport a molecule, or I guess any particular molecule, can be much more than we're going to actually calculate here, but it is typical to use an average velocity. And in this case, since we already know the volumetric flow rate from our previous equation, or our previous example, we know that we had 20 cubic meters per second mixing with 3 cubic meters per second. So totally we have 23 cubic meters per second, right? And so if we take our cross-sectional area, we divide our volumetric flow rate by the cross-sectional area, we can get a pretty good assumption of the average velocity. In this case, 3.3 meters per second. So once we have that information, we can begin to use our first order decay equation. And this is going to be, once it's already derived, it's basically already more or less solved. You have your concentration is equal to your initial concentration times the exponential function to the negative decay rate times time. And decay rate is usually per day, and time, of course, once it needs to match, so it's going to be per day also, or in days. So we already know our initial concentration in this case is 10.9 milligrams per liter. And then we need to, typically you're going to look up a K value from literature. Otherwise, you won't have to determine it empirically through, laboratory analysis. So in this case, let's take a look at benzene, common constituent of concern. It's been looked at many times in the past. There's a lot of K values for it. In this case, I got this one from a literature review. And now the K value is going to be dependent also on your environmental conditions. In this case, we're looking at, I think these are some average values for aerobic, or in other words, oxygenated conditions, of 3.35 per day. And then we need to solve for time. So in this case, it's just going to be our distance divided by our velocity. In other words, how long is it going to take to travel the 50 kilometers from point A to point B? And it's going to take almost 0.2 days. So once you have this information, it's basically just a plug and chug. We have our initial concentration here, the exponential function to the negative decay rate times the amount of time. And so we are able to find that our concentration at point B is 10.28 milligrams per liter, or in other words, there's a loss of 0.62 milligrams per liter. So for this flow, this relatively fast flowing stream, you're really not getting a lot of mitigation or decay of benzene between these 2 points. So if you were worried about contact, or some kind of exposure at point B, you would probably still be concerned. Okay, so let's take a moment. If that was all you're interested in, great, thanks. I hope that was helpful. But if you are interested in seeing how to derive the first order equation, then we can take a quick look at some differential equations here. So the basic kind of equation for determining the rate of decay, or in other words, balancing these mass balances, is that you have your change in concentration with respect to time is going to be equal to your concentration times your decay rate, right? And that's kind of what we were already talking about, where the concentration, the rate of decay is going to be proportional to the concentration, right? So we can separate these variables. So we're going to basically use the separation of variables method here, where we are going to move dt to one side and concentration to the other, and then we can integrate both sides. And since this is essentially 1 over c, the integral of 1 over c, of course, is in natural log of c, is equal to, this will become kt, right? The integral of dt will be t. So you have kt plus some constant. Usually this would be c in most arbitrary examples, but since we're already using concentration, in this case we're going to use b as our constant, and then we want to solve b for our boundary conditions. And in this case, we're going to be looking at when you have time equals 0, right? At the exact moment of mixing, in this case, right? What do we know? Well, we know that the concentration is going to be our initial concentration of 10.9 that we already knew we were starting with. So we're able to substitute our initial concentration and then setting the time to 0, then we know that our constant b is just the natural log of our initial concentration. So substituting our initial concentration back in for b, we have here, rewritten the equation, substituting what we've solved for b, and then separating or rewriting this, getting our natural logs together. Then it's probably apparent that the way to continue solving this is to multiply it by an exponential function. That's going to cancel out the natural log, and that's why, going back here, you get this e to the negative kt, and the natural log is gone. And then if you simply rearrange this solving for c, then you have c equals c naught e to the negative kt. So that's how we derive that type of equation. I think that's it. I appreciate you watching. I hope that was helpful, and I'll see you guys in the next one.